Hello everyone. Welcome to our presentation on language-guided exploration for RL agents in text environments. My name is Hitesh and my co-authors are Sahil Yerawar, Dhruvesh Patel, Soham Dan and Keerthiram Murugesan. Me, Sahil and Dhruvesh are graduate students from University of Massachusetts. Soham and Keerthiram are research scientists from IBM Research. Let's start with our presentation. A lot of real world tasks where we want to employ AI agents actually require sequential decision making. These tasks could be using language models to to use APIs and tools to perform some very specific tasks. It could be making recommendations for users or goal oriented conversational agents. These kinds of tasks require sequential decision making, and hence RL comes up as a first choice to model these problems. However, vanilla RL agents cannot do very complex reasoning without any priors. Also, they may require a lot of trials to learn in these kinds of environments. And that's where LLMs come to rescue. While they are not exactly known to model sequential decision making, however, they are very good at complex reasoning when these tasks are presented as language to them, and also they do perform really well even on limited trials. So, the basis of our work is how do we use these large language models to become priors to train RL agents to solve tasks in real world which can be modeled as sequential decision making tasks. We use the backdrop of text based games to actually test out our hypothesis and our framework. Both for real world problems, which are sequential decision making in nature, as well as text based games, reinforcement learning comes up as the first choice. Environments in the real world can also be modeled as partially observable Markov decision processes, and then the goal becomes to learn a policy to maximize long term rewards. In our work, we call the RL agent the explorer. In these text environments, agents can face very large action spaces. This is because as the episode goes on, the agent discovers a lot of objects, and the number of possible actions that it can take from all these objects keeps increasing combinatorically. Hence, if the exploration of all possible actions is done in an unguided fashion, it's very difficult for such agents to stumble over rewards which may be really sparse and thus foster learning. Hence, we need a way to eliminate such large number of choices. Now, one of the ways to reduce this large action space is to actually use common knowledge to understand which action is relevant for a given task and which action is irrelevant. Some actions may be relevant to the task at hand. For example, for boiling water, activating of the stove is a relevant action, and some actions are generic, which may be relevant to a lot of tasks. Some actions are irrelevant to a given task. For example, for the task of growing a plant, picking up of aluminum foil is irrelevant, and some tasks may be completely nonsensical. For example, the task to move fire pit to axe cannot be a sensible action. Hence, we use this basic idea to design a guide to help reduce the large action space for our explorer. So, how do we design a guide? Well, the idea of the guide is to map natural language instructions to relevant actions. That is, given a task description, can it say which action is relevant at runtime? Well, it can then be used to pre-filter actions for the Explorer. But doesn't the Explorer, which is the RL agent, also do something like this? Well, the Explorer tries to predict the best possible action at a given state of the agent. However, the guide is stateless. It tries to just eradicate the irrelevant actions for a given task description and doesn't depend on the state of the agent. This task is much simpler, and hence we show how well we are able to learn a guide to help our explorer. How do we train the guide? We use supervised contrastive learning to train the guide to align task descriptions to relevant actions. We want to learn a representation space where task descriptions are very close to actions which are relevant to it, and actions which are irrelevant are very far away. We create this data set using goal trajectories of agents in these environments to actually find tuples of a task description, an action from the goal set, and an action which was available in the environment but not part of the goal set. Once we train a guide on a large number of task description across tasks, we could now use it to help train the explorer by reducing its action space. While we can use any embedding language model as the guide, we experimented with BERT and found it to perform really well on unseen variations, and hence we chose the BERT as our language model for the guide. For the Explorer, we use DRRN as our RL agent. The DRRN it tries to learn the action value function by encoding the states and the action, and it then uses Q-learning to train to find a good policy with prioritized experience replay. The states are represented by the past observations, the state of the inventory, and whatever the agent can see at that point of time in the episode. The policy is stochastic during training and greedy at runtime. So how do we train the guide and the explorer together? First, we pre-train the guide using contrastive learning, and then it learns how to align task descriptions with relevant actions. After that, we train the explorer using the pre-trained guide. Now, the explorer, in our case, as we said, is trained using Q-learning, and at any time step in its episode, it invokes the guide with a probability 1 minus epsilon. Thus, the guide can help training of the explorer by making it choose from only relevant actions, and thus identifying states where it is able to get more rewards and thus learn good policies. So how do we choose this value of epsilon during training? One way could be to have a fixed epsilon where the guide is invoked 90% of time. The other is to have an increasing schedule of epsilon. That is, during the training of the explorer, the use of the guide is slowly weaned away. And this way of training is very similar to curriculum learning, where initially we handhold the explorer by allowing it to choose from only restricted set of actions picked by the guide, but slowly and slowly, as the training of the explorer progresses, we reduce the number of times the guide is invoked, thus making the explorer self-reliant. We report our numbers on both these forms of our framework, and we call this framework language guided exploration. We train and evaluate our language guided exploration framework on the ScienceWorld suite of environments. So it consists of 30 scientific text-based games where each of the games requires the agents to either learn or have as a prior common sense knowledge, procedural knowledge, and scientific knowledge. Also, the goal is to generalize to unseen variations. That every task in every of these 30 tasks have a lot of variations which are divided into train, dev, and test. And the idea is for the model to train itself on training variations and then evaluate on testing variations. These variations differ in critical task objects, in the starting location of the agent, and also the environmental objects that the agent encounters. Let us see some experimental results. First, we evaluate the guide on how well it is able to both rank ground truth actions as well as recall relevant actions. So we use the goal trajectories on a handheld validation set to evaluate our guide. We see that for k equals to 50, the guide is able to recall almost every valid action in these kinds of unseen variations. Thus, we choose like this value of k equals to 50 to select 50 best actions for training our explorer in our framework. So when we train the explorer along with our guide, our language guided exploration framework outperforms all the other complex methods like behavioral cloning, text decision transformer, and also DRRN. We see that it not only improves the episode scores in the cases where its episode scores are comparable to DRRN, it has better sample efficiency. And this could be coming from the way it allows the agent to identify relevant actions and thus either reach states that it was not able to reach, or even if it was able to reach after a long time of exploration, the exploration is speeding up very much by this framework, thus leading to better sample efficiency. In summary, tabular rasa RL agents struggle in environments because they have large action spaces and sparse rewards, hence learning by trial and error can be very difficult. Thus, we introduce a language prior called the guide, which helps these RL agents to explore in a much more informed manner. The way the guide helps the explorer is by pruning the action space using the task description. The guide is pre-trained using contrastive learning framework to learn an representation space where the task description is very close to relevant actions and very far away from irrelevant actions. We use this guide to train the explorer, and we see that our approach surpasses all the RL baselines like DRRN, text decision transformer, CALM, behavioral cloning on the science world environment. Thank you for joining for our presentation. We hope that you found our talk interesting and insightful. We appreciate your interest in this field and we hope to see you at the conference.